So now we'll put it all together. Here I've got a spherical soap bubble with the forces acting inwards, as we described before. And there's a volume of air, and there's a film of the soap water solution around it. And in general, in physics, things want to be in the most stable, low energy state possible. So to minimize all these forces, what's going to happen is it's going to want to form the minimal surface area to minimize all these forces. And the minimum surface area to enclose a given volume of air is going to be a sphere. And that is why we get spherical soap bubbles. And then gravity pulls the soap bubbles down and it hits the table. And what happens is there's no longer a need for a film down here because there's a table. So what happens is that spherical soap bubble hits the table. It's got the same volume of air, so it's just allowed to expand. And now we want to minimize the surface area about that table, and that's going to be a hemisphere. So it's important to note that we have equal volumes of air, and that'll lead to our next question. Now for the three questions. This was the bubble on the table that I measured before. It had a diameter of about 14 centimeters, a radius of 7 centimeters. It came from an original bubble. The radius we don't know. Here's the three questions. 1, find the exact relationship between the radius of any sphere and any hemisphere for the same volume. So it's not involving these numbers, it's just a general formula. Then, number 2, find the exact radius of the original bubble in this problem above that resulted in that hemisphere there. And then 3, find an approximate radius of the original bubble above. So see if you can answer those three questions.